This video is going to look at Newton's law of gravitation, or in other words, how do we actually calculate how strong gravity is if we're not close to the surface of the Earth. So let's jump into it. Newton's law of gravity says that all objects with mass attract every other object through the gravitational force. So I will pull on my computer monitor in front of me with the gravitational force. The Earth pulls me down with the gravitational force. I pull the Earth up with the gravitational force. If we were in the same room, you would pull on me with the gravitational force. I would pull on you with the gravitational force. That's because in all of those examples, the objects have mass. The equation to figure out how strong that pull is as follows. Fg equals big G m1 m2 over r squared. So in this setup, this is obviously the force of gravity. So that's what we're solving for. G is the universal gravitational constant. So universal gravitational constant. The m1 and m2 are the masses of the objects. And r is the radius, which is the distance between center of mass of objects. That's a long way of saying it's how far apart the objects are, but specifically how far apart the middles of the objects are. So for me, standing on the surface of the Earth, the distance isn't 0, although I am touching the Earth. The distance is from my center of mass, which is going to be roughly in the middle of my chest, all the way to the center of the Earth. So it's effectively the radius of the Earth. That value of G, big G here, is making sure I write this down correctly. 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. So in other words, because of this 10 to the negative 11th, unless you've got a lot of mass or you're very, very close together, the force is basically nothing. So if you imagine two people, let's just estimate their masses to be about 100 kilograms each, because that'll make our numbers easy. Say they're 1 meter apart. You have 100 times 6.67 times 10 to the negative 11th. So 100 squared is going to be 10 to the second squared, which would be 10 to the fourth. So we're looking at two people, 1 meter apart. The force is about 10 to the negative 7th newtons, roughly. We're not going to get exact numbers, but it's going to be around that size. How big is that? That is 0.0000001, right? Yeah, newtons. And just for reference, 100 grams, the weight of 100 grams, is equal to 100, so that's 0.1 times 10. That's about a newton, if I'm doing that math right. 100 times 10 divided by 1,000, yeah. So 1 newton is about how heavy if you hold 100 grams in your hand. Not much. So we're talking about, 7 times, like 7 powers of 10 smaller than the weight of 100 grams. So it's functionally 0. Unless you're getting up to the size of like planets, the amount of gravitational force is very, very tiny. And even if you have tiny distances like centimeters, that still doesn't make this force large enough to matter. So if we want to go to like a different planet here, then the force of gravity will change because the mass and the distance to the center of the planet will be different. So if you're standing on a different planet, the radius is different, the mass is different, so the gravitational force is different. So for example, if we wanted to find out our kind of Fg equals mg, but for the moon, we can do that here. So Fg equals 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. And that will be times the mass of the moon, so 7.35 times 10 to the 22nd kilograms, times whatever mass of the object you care about on the moon is. And the radius is going to be 1.74 times 10 to the 6th meters. And that will get squared. And if you run this through a calculator, let me pull up what that was. Run this through a calculator, you're going to get about 1.62 times m. So in other words, the mass or the weight on the moon is about 1.62 times m, and that compares to, on Earth, 9.8 m. So in other words, when you look at that, it's, roughly an eighth, and that's because the moon has less mass and a smaller radius. But the less mass is ultimately what matters more. Now, what you'll often see on the AP test, just as a heads up, is they might say like a planet with r equaling to 1/2 r, and mass of the Earth and the mass equaling 5 times the mass of the Earth. And they might say, how does the gravitational force compare? Well, it's pretty straightforward. You just plug those numbers in. So 5 times the mass of the Earth times m2 over 1/2 r Earth squared. And we'll get 5 over 4 me m2 over re, and re squared. And this is just the normal gravitational force we'd expect to see. Oh, sorry, I'm missing g on here. This is just the normal gravitational force. So in other words, it's 5/4 Earth's gravity. And there's all sorts of ways they can ask this type of problem of if you've got half the radius and you want the same amount of force, what does the mass need to be? If you've got, 2/3 the mass, how do you need to change the radius to get the same amount of force or to get twice the force? And it's all just setting up proportionalities, combining them, and kind of looking at the end result there. So that should kind of cover gravity and the strength of gravity on other planets.